right, we've come to our last set of notes for Unit 2, which means that we are approaching the test date. So please keep in mind that if you need to go back and rewatch any videos, if you need to stay after for help, please do so. Tonight's notes cover the topic of symmetry, which is something that we've talked about in previous years. And it's basically the ability of any figure to be transformed in some way so that the image will map onto itself. Okay, so letters like the letter H and the letter N have symmetry, while the letter P does not have symmetry. We have two types of symmetry. We have what's called reflectional or line symmetry, and this is where a figure can be mapped onto itself by a reflection in a line. So we have some figures right here. These all contain reflectional symmetry, whereas, sorry, so there's one line of symmetry through the capital letter A. Whoops, like this was not the best idea on my part. A butterfly has line symmetry, and so does the star. Okay. That's the most common type of symmetry. The letter H has reflectional symmetry, but we actually have one other type of symmetry. It's called rotational symmetry, and this is where a figure can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure, meaning if we rotate it around the center, the exact center, then we could turn it and have the figure actually stay exactly the same. So for example, if I were to turn this recycling symbol 120 degrees, do you see how we get the exact original figure? That's an example of rotational symmetry. With this one, we have rotational symmetry when we rotate it exactly 180 degrees. And for this one, we have to kind of use our imagination like the star is actually all the same. But we can rotate it and have the star map onto itself as long as we rotate it the right number of degrees. Okay, so line symmetry, also known as reflectional symmetry, and then rotational symmetry. So the letter N up here, the capital letter N, this actually doesn't have line symmetry. What it has is rotational symmetry. So some figures can have both reflectional and rotational symmetry. Some can just have one, and some figures like the letter P have neither reflectional nor rotational symmetry. Point symmetry is a specific type of rotational symmetry where the figure can be rotated exactly 180 degrees and only 180 degrees. So this kind of like banner or flag shape, this shape has point symmetry. And finally, a tessellation is a pattern of one or more figures that covers a plane with no gaps or overlaps. The most common example of this in the real world are tiles, tile floors, tile walls, things like that, where the tiles fit together perfectly and there are no gaps in the tiles and there are no places where the tiles overlap each other. This is a picture of a tessellation. You don't have to use this one, obviously, it's very complicated. You can use just create like a tile formation that you have in your home of squares or rectangles, something like that. We have a few different types of tessellations. The first one is what we call a pure tessellation. This is a tessellation that consists of only one type of figure. So if we take a look up here, these are all whatever they are, elephants or rhinoceros or whatever, but they're all the same exact figure. That's a pure tessellation. We also have what we call a regular tessellation, which is a tessellation that consists of only regular polygons, meaning that they're all congruent. So this is a regular tessellation that's not pure because we have two different types of shapes. We have octagons and squares, but the octagons and the squares are both regular figures. So that's a regular tessellation. We have a semi-regular tessellation where at least one polygon in the tessellation is regular and one is irregular. So here we have squares and kind of these diamonds and triangles. So the diamonds would be an irregular polygon where the squares, and it looks like it's hard to tell if the triangles are regular or irregular, but where we have at least one regular and one irregular. And then we have an irregular tessellation, which is where all the figures in it are irregular polygons. So hopefully those are pretty straightforward. We're almost done. The last thing that you need to know, and this is hugely important, and then I'm going to let you guys go, the only polygons that tessellate are, at least by themselves, the only polygons that will create a pure tessellation by themselves are any type of triangle, any type of quadrilateral, and only regular hexagons. And we'll talk a little bit more about the properties of a polygon that allows it to tessellate versus to not tessellate.